You ever wonder how your phone instantly recognizes your face? Or how a streaming service just knows what you want to watch next? Well, I can tell you, it's not magic, it's math. And today, we are pulling back the curtain on the secret language that pretty much powers our entire digital world.
I mean, really, think about it. How does an AI see a face or understand your voice commands? It doesn't have eyes or ears like we do, right? So it has to do something else. It has to translate all that rich, complex stuff, all the light, the shapes, the sound waves, into a language it can actually work with. And that language is the language of numbers.
And it turns out, just like Professor Jyotsna Grover puts it here, it doesn't matter what it is, an image made of pixels, the sound of your voice, even the words in an email. It all gets broken down, it all gets organized, and everything, literally everything, in the digital world ultimately boils down to one single powerful mathematical structure.
And yep, you guessed it. That tool is the Matrix. And no, I'm not talking about the movie, though honestly, it's just as fundamental to building these digital worlds we live in. This is the organizational powerhouse that lets computers wrangle just insane amounts of information. All right, so let's get into it. What exactly is a matrix? Let's meet the building blocks of data.
So, at the end of the day, a matrix is really just a rectangular grid of numbers. That's it. It's just a bunch of numbers arranged in rows and columns. The absolute best way to picture it? Think of a spreadsheet, but, for math. It's basically just a super organized box for holding data.
Okay, let's break down the anatomy here. See all those numbers inside the brackets? Each one is called an entry. The lines going across, the horizontal ones, those are your rows. And the ones going up and down, the vertical ones, those are the columns. Super simple, right? And here's a key thing. We always talk about the size as rows by columns. So if it has 2 rows and 3 columns, we call it a 2 by 3 matrix.
Okay, but what happens if a matrix gets really, really skinny? Like so skinny it only has one single row or one single column? Well, that has a special name. We call it a vector. It's technically a type of matrix, just a super simplified one. And trust me, it's incredibly important.
So why do we care about these vectors? Well, because they are the perfect way to represent one single thing, one data point. For example, let's say you're looking at a house. You could have one vector that holds all its important features. Number of bedrooms, square footage, maybe price, all in one neat little package. It keeps all the data for that one house perfectly organized.
Okay, so storing data is one thing. That's cool. But the real power, the real magic, comes from what we can actually do with these matrices. So let's open up the toolbox and look at the 2 most basic operations, adding and multiplying.
Now, addition is, honestly, super straightforward. There's really only one rule you have to remember. The 2 matrices you want to add have to be the exact same size. Same number of rows, same number of columns. If they are, you just add the numbers that are in the same spot. Top left number adds to the other top left number, bottom right to bottom right. That's it. Easy peasy.
But multiplication. Now this is where things get really interesting and a little weird. This is the part where you kind of have to forget the simple rules of arithmetic you learned in school. Matrix multiplication is unbelievably powerful, but it plays by its own set of rules.
You know how with regular numbers you can just multiply anything, right? 2 times 3. No big deal. Well, with matrices, nope. There is a very strict rule. The number of columns in the first matrix absolutely must equal the number of rows in the second one. If they don't match, you just can't multiply them. End of story.
There's a really easy way to see this. If you write down the sizes next to each other, like m by n and n by p, just look at the 2 numbers on the inside. Those have to be the same. So if you have a 3 by 2 matrix and a 2 by 5 matrix, see how the inner numbers are both 2? That's a match. It works. And the cool part is the size of your new matrix will be the outer numbers, in this case, 3 by 5.
So how does the actual calculation work? Well, it's this kind of row-on-column dance. To get just one number in your final answer, you take an entire row from the first matrix and you multiply it piece by piece with an entire column from the second matrix. Then you add all those little products up. It's a whole process, and you can see that flow perfectly here with the arrows.
Okay, so this whole weird multiplication process, it leads to a really, really surprising result. It actually breaks one of the most fundamental rules of math that I promise you learned back in elementary school and have taken for granted ever since.
Okay, quick pop quiz. What's 5 times 4? It's 20, right? And what's 4 times 5? Also 20. The order doesn't matter. That's called being commutative. So the big question is, does that rule work for matrices? Can you just multiply A times B and then flip it to B times A and get the same answer? And the answer, get ready for this, is a huge emphatic no. For matrices, A times B is almost never the same as B times A. In fact, a lot of the time if you flip them, you can't even do the multiplication anymore. This is a really mind-bending idea, but it's so important. Matrix multiplication is not commutative. The order is everything. And that's actually the secret sauce behind so many cool things like 3D graphics and complex simulations. All right, we've got the pieces, we've got the tools. So what's the point? How do we use all this stuff to solve actual messy real-world problems? This is where we go from abstract math to a straight-up problem-solving machine. So a ton of really complex problems, I'm talking everything from supply chain logistics to financial modeling, can be boiled down into what's called a system of linear equations. And when you first look at it, it just looks like a tangled mess, right? A total jumble of x's and y's. The whole challenge is finding that one magic set of values for all the variables that makes every single equation true at the same time. And this is where the matrix swoops in to save the day. We can take that whole chaotic mass of equations and neatly pack it into a single organized structure called an augmented matrix. It just strips out all the numbers, the coefficients, and puts them in a grid, separating them from the answers. It literally brings order from chaos. So now that it's all organized, we can solve it. And we solve it like a puzzle, using just 3 simple legal moves. They're called elementary row operations. Here are the rules. 1. You can swap any 2 rows. 2. You can multiply an entire row by any number that isn't 0. And 3. You can add a multiple of one row to another row. That's it. Those 3 moves are all you need to solve the entire system. And by using those 3 simple rules over and over again, you can systematically chip away at the problem. You can transform that complex matrix on the left into the beautifully simple, solved version on the right. That's called row echelon form. See that neat triangle of zeros it creates? That process basically untangles everything and just hands you the answer. It's an incredibly powerful way to solve what looked like an impossible problem. So let's bring this all home. Why does any of this matter? Well, first, matrices are the fundamental language computers use to understand data. They provide the structure. Second, the operations we talked about, especially that weird multiplication, are the actions. They let us manipulate and analyze that data on a huge scale. And when you put those 2 things together, you get an unbelievably powerful system for solving incredibly complex, real-world problems. You know, all those simple building blocks we just looked at, they scale up. The very same ideas are used to build the absolutely colossal matrices that power today's AI. We're talking matrices with billions, even trillions of entries. They are, without a doubt, the foundation of our modern world. So the only real question left is, what problems will you solve with them?